All right, our last little pre-lecture for bacterial growth is going to be some of the bacterial growth equations and applications of those equations. So one thing that we see when we look at bacterial growth is what's called a Monod equation. And the Monod equation is used when we're looking at growth rate related to substrate concentration. So this is particularly important in wastewater treatment. We know that the amount of substrate that we have is going to tell us how fast we move in the exponential phase and whether or not we move out of exponential phase to stationary and then death phase. So what the Monod equation does is it characterizes using specific growth rate how substrate is related to growth in the system. So in the Monod equation, a mu is the specific growth rate, but a mu max is the maximum growth rate. S is going to represent substrate concentration, and this could be mass per volume, so milligrams per liter is very common. And then Ks is what's called an affinity constant, and this relates the specific microorganism to the substrate. So on this graph over here, we plot substrate concentration versus specific growth. And as the affinity constant is greater than the substrate itself, the specific growth is actually pretty low. But as the substrate is greater than the affinity constant, that specific growth rate is going to be higher and it's going to approach this maximum. So this is an equation that is actually used to design wastewater treatment plants when we look at how much wastewater is being fed, because wastewater is a substrate for microorganisms. So two limiting cases that we just talked about, right? The substrate is greater than the affinity constant. If that's the case, our equation would simplify to a change in number of cells per time would be equal to the max specific growth rate times the number of cells. So in that condition, growth will occur at the maximum growth rate. Very few instances where that actually occurs in real life, right? Or we have enough substrate. We are always limited by substrate in real life, so this condition is almost never met. But if our affinity constant is greater than our substrate, this is very common. And in this case, our equation looks a little bit different. It's a dx dt equals the max growth rate times the amount of substrate times the number of cells divided by the affinity constant. And when the substrate concentration is low, growth is dependent on the substrate concentration. That's effectively what this is saying here, right? This is also the type of growth that would be more typically expected, found under natural conditions, because substrate and nutrients are always limiting in the natural world. So in the Monod equation, there's always constants that we need to use. So this is going to be part of your pre-lecture questions, is figuring out what growth temperatures and limiting nutrients and maximum growth rates and so on and so forth are related to specific organisms. So these are intrinsic properties related to specific organisms. And it looks at, how are we able to basically grow these organisms the best. Now, this is a very, very small fraction of the organisms that exist in the world, but they are very, very well defined because these are very easy organisms to culture. We can also write the Monod equation in a slightly different way, and this is the way that you'll start to see it if you move into advanced wastewater treatment, is we can relate it to substrate utilization. So substrate utilization is defined as ds dt, and that's equal to -1 over y times dx dt. So remember, dx dt is the change in the number of cells per time, and y is what's called a cell yield. So the cell yield is a coefficient that's defined as the unit amount of cell mass produced per the unit amount of substrate consumed. It's basically a way of getting your units to work out. How much cell mass do you produce for every amount of substrate consumed in the system? Okay, it's dependent upon the structure of the substrate being utilized and any intrinsic physiological properties of whatever organism is using it. So we're not going to worry too much about cell yield in this class or do a whole lot of calculations related to cell yield, but it is something that becomes more and more important as we think about wastewater treatment. So one of the most critical graphs that I want to show you for this class is the relationship between substrate and cell mass. So we've got time on the x-axis and substrate concentration in terms of milligrams per liter on the y-axis. And many times in a wastewater system, this is the concentration of BOD5, which you should have heard of hopefully before in one of your other environmental engineering courses. And the equation that you're seeing on the right is just that full expression of the substrate utilization using cell yield and using what we know about dx/dt. It's just putting all the equations you've seen before together. And it looks very complicated, but in most cases, we're going to have most of the information for this. But the critical thing about this graph that I want you to see is that this part right here of the cell mass, that is exponential growth. And then substrate, when we have enough substrate, you can see we're in the lag phase, but the substrate drops off exponentially as the cells are growing exponentially. So this point right here where the two graphs meet is actually the sweet spot of where we want to be if we are using microorganisms for environmental reactors. The reason for that is that we want to apply substrate at a rate that allows the microorganisms to continue to grow without getting to stationary phase or falling back into lag phase. So we want just enough substrate applied to make sure that cells continue to stay in the exponential phase and divide and continue to grow in the system. If we move into stationary phase or death phase, we end up killing our reactor off, which is not a good thing in real world. Right, so there's the relevance, right, to environmental engineers, right? The phase that matters the most is the exponential phase most of the time, but it does depend. For aerobic and anaerobic wastewater digesters, we want to be in exponential phase, and that's because if we have organisms in death phase, we don't have organisms that are viable or alive to have substrate removal. If all the organisms die, we accumulate wastewater in our system, and that's not good. So the next couple slides are going to be an example of what this looks like in wastewater. Don't worry about the specifics of this because you haven't taken a class in wastewater treatment yet, but I want to show you the application because it is very, very relevant to us as environmental engineers. So one process that uses this principle is called an activated sludge process. It uses aerobic microorganisms, and it takes the sludge and it takes the waste from a specific reactor and it cycles it through aeration to get enough air in it, and then we remove solids and we have what's called activated sludge, and this actually has microorganisms in it. So we feed a specific amount of substrate into this system, and this activated sludge is called activated because it's actually biologically active, and those organisms are going to eat the substrate. And the way that we feed back into this system, remember this is a recycle line from your mass and balance class, right? The way that we feed that amount of substrate into the system is actually very, very optimized depending upon being in exponential growth phase. So that's part of its relevance to us, right? And we know, right, from doing all of this biology that we're starting to learn is that we're going to have organic matter and oxygen, and in the presence of organisms, we get new cells, energy, CO2, water, other end products, right? And this is actually the reaction, right? This is cellular respiration, aerobic cellular respiration. This is what happens in an activated sludge system. So this is just a slide that I pulled from CIVI 420. It's a water and wastewater treatment design course. And it just gives you a little bit more context that, you know, we're really using these equations. We're optimizing bacterial growth specifically to remove wastewater. And this is the same graph, right? This is concentration of BOD versus time. And we see that the cell mass goes up and declines as the substrate goes down. So this is a substrate utilization curve, and that sweet spot is right where the two meet, right? And this comes from a wastewater treatment design manual. This is not from a biology textbook, right? So understanding that cell growth is going to be really, really critical for the designs of those types of reactors. Okay, there's also some modified versions of these equations. So the Michaelis-Menten equation is just a variation of the Monod equation. So it's meant to specifically represent how substrate is utilized in wastewater treatment plants. And so I just want to pop this up here, not because I want you to memorize this equation, but because it's really important to see that there is a huge connection between environmental microbiology and learning bacterial growth to the actual application of designing zero order and first order reactors. Okay, so this is just an example of the types of equations that get used in wastewater treatment design, but it's all based on what you're learning in this class about microbiology. Okay, and just like the Monod equation, right, there are many possible types of substrates in wastewater. So this gives you a sense of what type of wastewater might be coming in, what type of reaction might be happening, and what is the reaction rate constant. And all of these are derived based on knowing BOD, TOC, types of substrate, types of organisms, all that stuff. So again, this slide is meant to be illustrative of an application of what you're learning. Okay, last thing I want to do in this video, because I know we're getting long and we've had a lot of videos so far, is to start with a calculation of the number of cells in pure culture. So what I'm going to recommend is that you pause the video and try this for yourself, and then look at the solution later in the video. So if we start with 10,000 cells in a culture, we have a generation time of 2 hours. We want to know how many cells will be in the culture after 4 hours, 24 hours, and 48 hours. So take a pause, try this yourself, and then look at the solution. All right, I hope you took that pause. So what we want to do is we want to use the exponential growth equation right here, where x naught is the initial number of cells and n is the number of generations, and we want to know what x is after a certain number of generations. So what we need to do basically every time is just apply this equation as it is. We know that we start with 10 to the 4th cells, and it's basically the n that's changing, right? We know that after 4 hours, right, there's 2 hours per generation. So after 2 generations, we're going to get 4 times 10 to the 4th cells. So we basically need to figure out how many generations happen within 4 hours, and then figure out how many generations are associated with each of these time steps to figure out the number of cells. So what this shows you is that there's an increase of less than 1 order of magnitude for 4 hours, but over 3 orders of magnitudes over 4 hours. So what this shows you is it really shows you just how many cells are being generated in a very, very short time, but that the number of generations does matter. Okay, so take some time to look at this equation and this calculation. We're going to go over something very, very similar in class. If this doesn't make sense, please come in with questions. And that's going to wrap us out for this pre-lecture.